information is, right? So as you might have guessed, we'll be dealing with like random variables and random numbers and probability distributions a lot. Okay, so let's say there is an event. Let's say I'm giving you a statement. The university is going to be open next week. Would you say the probability of that happening is 1?
Yeah, pretty close to 1.
Yeah. Close to 1, right? Yeah. But not 1. Lots of things can happen, right? So but if somebody tells you, or somebody's talking and you're listening into the gossip, and you found out that the university is going to be open next week, did you get a lot of information from that? From what you heard, right? But if you hear university is going to be closed next week, would you say you got a lot of information from that gossip? So what are we learning here? That means the less likely a event is to happen, observing that event will give you more information, right? If the probability of event happening is smaller, is low, then if you observe this event, then you have large amount of information, right? So that's the intuition. So obviously, so what we're gonna do is we're gonna measure information in terms of the probability of an event, right? I'm saying, okay, if you observe an event, how much information did you get? That information is a function of its probability. And also we know it's an inverse function of the probability. That is, the probability goes down, the amount of information should go up. Okay, there can be many functions which are like that.
So you're saying like the less likelihood of something happening, the more information you're going to get out of that event.
That's right.
So basically, you get more information out of a mistake than actually doing.
What do you mean a mistake?
So say you go and you make a mistake and you're learning avenues around the actual problem, whereas you were just given the right answer, you were just immediately taken to it.
I see what you're getting, but that's probably not the right analogy. So it may be closer to the right analogy if the mistakes are rare. Okay, if mistakes are rare, and then that rare event happens, then you get a lot of information from it. But if everything goes on routine, then you don't get anything, right? You see what I'm saying? Okay, so now, all right, so I know my information is a function. Let's say there's an event A. Okay, so the information from observing that event A is a function of the probability of A. Okay, and I also know f is a decreasing function. That means if the probability goes up, I should get a smaller function, right? Okay, so now can you guys give me some examples of this f?
You could do like a line that just goes down. You could do an exponential that's an inverse exponential.
Okay, so let's see, Tito, one of the example Tito is giving is maybe e to the minus p of a. So that's a decreasing function of probability. Any other examples?
1 minus x. Yeah.
1 minus x, let's say equal 1 minus p of a. Okay, any other? So 1 minus p of a is just this, which is also what Tito was saying, right? This is something looks like that. Any other functions? Okay, so how about 1 over p of a? How about log of 1 over p of a? All of these are valid, right? Okay. So, and there can be infinite different functions like this. All of them are valid. All right. So just by this intuition doesn't let us help us corner down the function, right? So let's talk about something else. Let's say you observe two independent events. Okay. So let's say you observed event A, you got some information. Let's say if let's say event A and B, let's use capital letters from now on. A and B are independent. Okay. So and then I of A is the information you get when you observe A. And then I of B is the information you get when you observe B. Okay, so if you observe both A and B happening, okay, then how would you think this should be related to these individual informations? Right, so this is the amount of information you get from event A, this is the amount of information you get from B. Now you're observing both of them and they're both independent informations. Intuitively, how would you say this would be should be related to this individual information? Sum, right? That's a very common intuition, right? So if they're all, but only if they're independent, right? If they're not independent, it may not be the sum of them. But if they're independent and then you're observing both events, you get the sum of information. Right? So you say I of A plus I of B. Right? But there is no right answer, right? This is just our intuition. That's what we feel like it should be. Okay, so now, but we know this I is really a function of my probabilities, right? So this is P of A intersection B, right? I'm saying it should be equal to F of P of A plus F of P of B, right? Now, if A and B are independent, what is the relationship between P of A intersection B and P of A, P of B?
Should be less than equal.
See, the question is, if let's say A and B are independent, not mutually exclusive, they are independent. Mutually exclusive means they're very highly dependent on each other, right? If one happens, the other does not happen, so they're not independent. Okay, so A and B are independent. I'm asking you, what is the relationship between probability of A intersection B in terms of P of A and P of B?
Zero.
What is zero?
The probability of A and B existing, right? Because they're independent, so you can't have.
So you're saying probability of A and B is zero? If A and B are independent, you're saying both happening are, you know, both cannot happen at the same time?
Would it be like probably
Yeah, I'm thinking the intersection. I'm like,
we have to do like a conditional, like given statement type.
Okay, so according to our multiplication rule, this is P of A times P of B given A. Right? If A and B are independent, what is P of B given A in terms of P of B? By definition. Okay? With this in the previous week. Okay? So now, what I'm saying is my F of P of A intersection B is equal to F of P of A times F of P of B, right? So let me simplify the notation a little bit. What I'm really saying is F of X times Y, or X multiplied by Y. I'm replacing P of A intersection B with P of A times P of B. Right? So let me actually write that. P of A times P of B is equal to F of P of A times P of B. Times F of P of B. So to simplify the notation a little bit, I'll say X equal to P of A, Y equal to P of B. Right? So then what I'm really saying is F of X, Y is equal to F of X times F of Y. Wait, I think let's see. What you're saying is I of A intersection B should be I of A plus I of B, right? So this should be plus here. With me? I see blank faces. All right, let's do this again. So I said A of A intersection B. So I of A intersection B should be I of A plus I of B, right? That means saying I of P of A intersection B, or sorry, F will be equal to F of P of A plus F of P of B. With me? And that means F of P of A times P of P, because A and B are independent, should be equal to F of P of A plus F of P of P. Right, now I'm going to write X equal to P of A, Y equal to P of P. So I'm getting F of XY is equal to F of X plus F of Y. Okay, Alex.
The only thing I don't understand is before we had said P of A intersection B was equal to probability of A times the probability of B, correct? So then why is it that I of A intersection B is equal to I A plus I B?
So this is where we started with, right? We said according to intuition, that's what I should be.
Oh, okay.
Right? So if you observe two independent events, the information you get from observing them jointly should be the sum of the information you get by observing them, individually.
Okay.
Right? So we started with, okay, intuitively this is what we feel like the information function should be. Right?
So your identity function is taking in events, but your F, whatever F is,
It's taking probabilities. Yeah. And then the way we are defining that is like this. Okay. Just. And this it's not identity, it's the information function.
Yeah, yeah.
Okay. All right. So we have now two properties, right? That we have two properties. One is we said our information should be a decreasing function of my probability, and it has to satisfy this equation. When we said it should be decreasing, we got some examples of F. Now on top of that, we are saying it should also, the F should also satisfy this equation here. So F should be decreasing function, and it should have this property. Okay, so now here's our first group exercise. Divide into groups of maybe 3, right? So among all these functions, which of them satisfies f of xy is equal to f of x plus f of y? Right, in here you want to treat p of a as the variable. Actually, one of them is the right answer, right? But only one of them is the right answer. Which of these functions satisfies that?
Oh yeah, it should be like yeah, it was very similar to the key.
So just as a hint, what this means is like f of x is equal to e to the minus x. That's what that means, right?
Yeah. One thing times another thing, right? Probabilities. So probability of that's not exactly that. Well, so that's just like logarithmic properties are like if you have log of a over b.
No, yeah.
Oh yeah, but I did log a.
Good. Okay, answers. let's
then
call
just
these
put
A, B, C, and D.
This is that property.
Okay, and I'm looking for this property.
A logarithmic is.
How many say A?
You're right.
Okay, Joe. Anybody else?
It's because it's the one
Okay, how many say this is one vote here? How many say B? One here. How many say C? How many say D? Okay, lots of them. Okay, say maybe greater than 7. Okay. Okay. So people who said D, why D?
Because with the log function, whenever you add them, you multiply what's on the side.
Right. Okay. So let's see what Noel is saying here. So I said f of xy should be equal to f of x plus f of y. Right. So if f of x is equal to log 1 over x, right, then f of x comma y, x times y will be equal to log 1 over xy. It will be equal to log 1 over x plus log 1 over y. Right? So this should be equal to f of x plus f of y. Okay? And if you have f of x is log 1 over x, is f of x a decreasing function of x? If x increases, f of x decreases. Right? Because 1 over x decreases. And logarithm is a monotonically increasing function. Right? So now we have this nice property. So if f of x is log 1 over x, then f is decreasing in x, and it has this nice property that when you multiply these two, you get the sum, right? So then if my f of x is 1 over x, that means if the information I get from observing an event A, if I define it, okay, if I define it like this, log 1 over p of A, then this particular definition of my information satisfies those two intuitive properties. Right? The intuitive properties is if the probability of event A happening is low, then by observing A I should get a lot of information. Right? Or if the probability of event as happening is high, by observing it I shouldn't get much information. Right? That's the inverse. That's one intuition. And if there are two independent events, then the information I get by observing both of them should be the sum of information I get by observing them individually. This particular function satisfies both those intuitive properties. Okay, so therefore this is how we're going to define our information. Okay,
What is A in this case?
A is an event.
So just some
Event.
information about the event.
Right. Okay. So from our data perspective, event would be you observe a particular message coming out of the data set. That's the event. Like you observe you pulled out a letter, it's A.
Yeah.
That's an event. Right? Or if you pull out a letter, it's B. That's a different event. So, okay.
But that event is represented by log of 1 over px.
That's how we are going to define how much information there is in an event, or how much information you get by observing an event.
What do you mean by information?
This is the definition. Okay. Good. All right. So we are really starting from a very abstract notion of information, right? In information, we have like a generic sense and meaning in English. But now we wanted to give it some very like mathematical properties of how to quantify it. Right? And so in order to give that some function, we started with, okay, intuitively it should satisfy these mathematical properties. And we found a function which actually does that. And so now we're saying that is how we're going to quantify it, because it said that function, if you quantify it this way, intuitively it makes sense. Right? Okay, so very soon we're going to use this particular definition to actually prove results on lower limits on compression. So the question is, okay, how can you start from intuition and then end up at like fundamental limits, right? Obviously the answer is there is more than intuition to it, and we'll prove that. Okay, so you can start with this very intuitive definitions and end up here, or you can also prove in some other way how much you can compress, and you'll also end up here. Or if you start from here, you could say, okay, that's the best you can compress. You can prove that. Okay, so we'll see that later. Any questions so far? I know this is starting from a very abstract sense, right? So, but as I said, we're going to talk about very abstract fundamental concepts. It's going to be abstract. Okay, so let's talk about another like concept in probability. It's called random variables. Okay, so how many of you have heard the term random variable before? Okay, pretty much everybody, because you have taken statistics, right? Okay, so random variable is just if you take a outcome from an experiment, and you assign a number to it. Okay, that's what a random variable does. Or you can, you for each outcome you assign a number, and you can extend that definition to events also. Okay, so what x is, a random variable x is a function from your set of all outcomes, which we denoted by omega, to real numbers. Okay, now how you extend that definition of a random variable from set of outcomes to events is somewhat flexible, but we have a standard definition of doing it, right? So the way we'll do that, let's say if there is an event A, then what x assigns to A is basically just the sum of all the elements A belongs to. A belongs to A, x of A. That's how we're going to assign that random variable number. Okay, but more importantly, what you want to figure out is, observe here is a random variable is something which assigns to each event a real number. And we can start with a basic definition of assigning a real number to each outcome, and using that definition you can extend it to all events. Okay, so if you look at here, information function, is information function a random variable? How many say yes? How many say no? Okay, people are saying no. Why no? Why is it not a random variable?
Because it's the variable in your question of outcomes. It's what's being questioned, so it's like a defined thing.
Okay, any other answers? Why is it not a random variable?
Because it contains all the possible outcomes.
What contains all the possible? A is just an event. Okay, again, how did we define a random variable? Random variable is something which assigns a number to an event, right? So this information function, is it assigning a number to an event?
Yes.
Is it a random variable?
Yes.
That's it. Okay, and you can have very nice definitions if you just assign random variable to each outcome. So let's say if A is an outcome instead of an event, right, then your random variable assigning a number to each outcome.
Why is it called a variable? Why is it called a random variable? Why is it just not called a variable?
Because what the number variable takes is random, because events happen randomly,
Okay.
right? So you can say, okay, what is the probability that this random variable takes that number? It's the probability of that outcome happening, right? It's like that. Okay, so let's let's look at a very simple example. Experiment: toss a coin. Okay, so my omega is heads and tails. Those are the set of all outcomes, right? And then I can define a random variable where I say x of h is equal to 1 and x of t is equal to 0. Okay, so that means probability, the random variable is assigning a number to each outcome. Okay, and I can also say what is the probability that x will be assigned 1. That will be equal to the probability that x or the probability of event heads. Okay, that's how it's not that complicated really. Because, and then random variables are useful because we have to deal with numbers instead of abstract outcomes or events, and we know how to deal with numbers. Right? Ultimately, that's what we're doing here, right? We want to we want to end up doing some quantification, so we'll always end up with random variables. Okay, so again in this one, information now here is a random variable, because if you're observing an experiment, you're observing different outcomes, right? Now depending on the probability of the outcome, you get different amount of information for each observation you're making. So the amount of information you're getting by observing that experiment is different for each outcome. It's random, right? That's why the information you're getting from that experiment is also random. So clear, everybody? Okay, see lots of very blank faces, which is not a very good sign. Okay, I'll probably give you guys a few minutes here to take a pause and see if you have any questions.
So random variables is just getting one variable number that we give to, like, Judah does for heads
this
was
symbol
equal
and
to
this
1,
symbol
tails
are
equal
not
to 0.
going to be the
It would
same.
be random information that would give
But
certain
I think
values,
like
or is information
that symbol is like
from
No, information is a specific example of a random variable.
Yeah.
You can have many other random variables.
So random variables cover a wide variety.
Any function which assigns a number to each outcome is a random variable.
I'm saying A
Is that
is going to
any
be
probability?
I think X is a subset of all sets.
The probability
Yes, you can treat it that way. Yes,
Right.
that's a very good point. Probability is a random variable, but we usually won't treat it as such, but it is.
all of the events and a map of
Okay,
like,
gotcha.
not that I don't think it creates a
It assigns a specific number to a specific outcome. Right.
X of A, which is a real event. There's an event.
Right. For a given outcome, you only have one number.
It's an associated number, which is going to be the sum of all these events where A is inside.
Which what?
That would be
So the real person would be a real number.
Sure. I mean, it's like a constant random variable, right? So let's say if x of heads was 1, x of tails was also 1, it's still a random variable, right? But it's like, like f of x equal to c is still a function of x.
3 times and then like stop or something.
In that case, it's like if you generally say f of x is a function that changes with x, right? And then f of x equal to c is also a function of x, though.
Yes.
It's like a very one degenerate case.
I'm not sure.
Any questions so far?
Can we do like one more example?
Sure. Okay. So let's say. All right. Let's do this experiment. Horse race. Right. There are 5 horses of different colors, like blue horse. Yeah, it's an imaginary horse, but okay, it's blue. There's a black horse. There's a green horse. There's a red horse, and there's a white horse. Okay, I mean there has to be a white horse, right? And there has to be a black horse, but everything else is imaginary horses. Okay. So, all right, and then I'll say, okay, if the white horse wins, I get $100. Okay, so that means x of w is 100, right? It's basic. I'm writing a shorthand here. If x of w means x of w wins. Okay, and then if blue horse wins, I get $200.
Blue or black?
Oh, sorry, black. Black horse wins, I get $200. If blue horse wins, I lose $100. Right? Green horse wins, I maybe $10,000. And the red horse wins, I lose $5,000. Okay.
High stakes.
All right. So that's now x is a random variable, right? And it's taking random values based on the outcomes of the event, outcomes of the experiment, right? Okay. So now here's a interesting question you can ask. Let's say there is a certain probability for these things to win, and you know what the probabilities are. Okay, so you know blue wins with a certain probability, black wins with a certain probability, and so on. Okay, so now you go to this horse race and you're betting every day, right? And you're playing every day. So what is the, on average, how much money are you winning? How would you calculate that? Right? On average, yeah. Let's assume that you know what the probabilities are. On average, how much money are you getting? Let's go again into groups. Give me the formula for average. Let's on average on every day. Let's say you go for 1,000 days. You add up all the money and then divide by 1,000. One race per day. And then give me the formula in terms of these probabilities and x of w, x of so on. Forget about these values. Just give me the formula in terms of probabilities and the random values.
Well, no, that doesn't make sense. Oh yeah, divided by no.
The total probability.
Well, it depends. If it's per day.
So
Let's say this is my omega now.
So just be cool.
You wouldn't do XU, because you would never want XU or XSR. So yeah, you would so in 2D, it's not that bad.
Okay, I see. All right, there is a. Let me slightly modify the question too, because it's not a complete question.
Okay.
So let's say you're going every day, right? And you're picking one horse at random.
Okay, good. I was like, I'm not betting on two of those horses.
Right. So I mean, this is a it's like the net result of how much you buy and how much you get and all this stuff. But it's not a very well formulated question, but if you just pick one horse at random every day, right? Oh no, it's okay. Sorry. All right, No, my original question was correct, right? So this is how you're playing it. You go to a race, you don't have to do anything, right? If blue horse wins, you get that money. That's it. Okay, that's it. You're not actively betting on anything. You just show up. If that wins, you get some money. That's it.
Yeah, this is what you're gonna get. This is the result. This
Right,
is the
exactly.
random variable that you're associated
Right.
with this.
Okay.
Probability stuff.
Right. So you just show up there. So for example, if you show up and a blue horse wins, you lose $100. Things like that.
yeah, but like But we can, from intuition, we can say like that green horse is probably like never gonna, like, it's pretty.
That's what weird look at that.
Yeah, it's a weird look at that. So.
Answers? Okay, what's the answer?
You just take that amount and multiply by the probability.
Probability, right? So what Noel is saying is, let's say blue horse wins with the probability P of U, right? When that happens, you get X of U money, right? Plus, black horse wins with the probability P of B. When that happens, you win X of B money, plus so on, right? So if you express this succinctly, you will get, okay, for each color in omega, right, then sum of C times X of C, right? That's the average number, average amount of money you will get. Okay, or in other words, that's the expected value of X. On average, that's the expected value of X. Okay, so this is called expectation of X. What would you expect the value of X would be? Right, you take the weighted average, and that's how we define it. Okay, and we're defining it like that, and empirically turns out to be that will be like the average. It will be very close to the average, okay, if you define it that way. Right, when I'm saying these terms, actually there's a lot of they're loaded statements. When I say I'm defining it like this, and it turns out to be that will be very close to the average, you know, that basically what I'm describing is the law of large numbers. Okay, so that's a loaded statement right there. Okay, so maybe you've heard this in terms of law of averages, right? So basically, if you define, in fact, some people define probabilities this way, right? The probability of event is, you know, you do 1 million times, experiment 1 million times, you count the number of times this event happens, and you know, that number of times divided by 1 million is the probability of that event. That's how some people define it. But most of the times you don't have a way of doing 1 million times the experiment, right? So you have to define probabilities without doing 1 million times. So that's a different way of defining probabilities, right? And there's a big, you know, you can have all these arguments. But let's say if I come and say, okay, this is the probability of this event, another person can say, okay, how do you know that's the probability? What do you mean by that? So I will say, hey, that means if we do this experiment 1 million times, you will get this, like this event 1,000 times. But then other guys, but you haven't done that experiment, how do you know? Right? So there is this whole, you know, like a sort of a big discussion among how do you define probabilities and so on, right? So most mathematicians just come starting with like mathematically, right? Hey, this is how I'm defining probability, just very purely. It's just a number between 0 and 1, and all the probabilities sum to 1. That's all there is to it, right? But if you do it properly, you can relate these probabilities to empirical fractions, you know, but that's a different story. Okay. Anyway, so that's probably a topic which can, you know, we can make our whole like full 2 classes on it. I'm not sure if you did that in your statistics class, but that's a different whole topic altogether. Okay, but this is how we are defining expectations, like the average value the random variable takes. Okay, so now let's go to our, let's say, information. Right, so now I can talk about what is the expected information I can get, or the average information I get from observing an experiment. Right, I'm observing experiments, I'm looking at outcomes of that experiment, I'm asking, okay, what is the average information I'm getting?
What is that notation?
It is E, expectation. Okay, so then this will just be equal to sigma over all events. A belongs to all outcomes, probability of that outcome times log of 1 over probability of that outcome. This one, yes, this one is I of A. Right? This is, according to the definition of our expectation, this should be P of A times I of A, right? That's the average value of I, and that will be by definition this. Okay, and this, the average value of I, or the average value of information, is called the entropy of that experiment. Okay, it's called entropy. How many of you have heard the term entropy in physics? Everybody, right? So second law of thermodynamics. It's defined very close to this. Okay, it's a very close definition of what the entropy in physics. But anyway, so if there's an experiment and these are all the possible outcomes as omega, each has a probability, then if you're asking the question what is the average amount of information you get from observing the experiment, that's the entropy. Okay, now in other words, entropy can also tell you how difficult it is to guess what's going to happen. Okay, so let's say there is an experiment where one of the outcome is certain. That means the probability of that event happening is 1, right? And the probability of all other events happening is 0. And then if you compute the entropy of that, it will turn out to be 0. Okay, that means you can, if there's an experiment where one of the outcome is certain, then you can pretty much guess what's going to happen, right? That means there is no randomness in the experiment. But if it's very difficult to guess what's going to happen, that means the experiment is very random, right? So the amount of randomness you measure with entropy. The higher the entropy, the difficult it is to guess. Okay, so now let's look at a uncompressed file versus a compressed file. Which one would you say the bits are difficult to guess, in the compressed file or the uncompressed file?
What do you mean
by if you look at one bit and you want to try and guess something about what the following bits are, right? Would it be easy to do it in the compressed file or the uncompressed file? The compressed file, it should be easier in the uncompressed file, right? Because in the uncompressed file there would be some patterns, and you can so if you can use those, if there are patterns, that means you can do some prediction, right? So but in the uncompressed file, you should not be able to predict anything. That means the entropy of your compressed file should be much higher than the entropy of the uncompressed files, right? In fact, you like taking an uncompressed file and you measure its entropy and you say, okay, that's how much I can compress it. Okay, right? Because that's how much information there is in that data set. Okay, let's say if there's a data set which is all ones, right? It is all ones. That means the entropy is 0, right? That means I don't need any information to store that, because if it's all ones, I don't need to really store it. And I know I can generate how many ones I want, so I don't really need to store it, right? So if there's a data set which is all ones, that means I don't need any bits to store it. But if it's all very random, that means I have to use lots of bits to store it. That's the intuition. The uncompressed file is low entropy, yes. Okay, so that's where we're gonna go. Any questions so far? Well, so we'll stop here.